Hope you're all keeping well. I've kind of dropped into this with a couple of weeks' notice, and it's it's a topic that I've been involved with respect to building new railways. And of course, there's a lot of talk around sustainability and decarbonisation in the industry, particularly in the PWI environment with renewals and maintenance. But this presentation is specifically around building new railways, and also at the early stages of a project, which is a very important stage from this point of view, because so many decisions are made in the early days. So building a new railway is a major undertaking, and there are many considerations in the feasibility stage before it can be deemed viable. So finding a corridor is an early activity to support a business case. So governments and other clients, such as developers, will not embark on a project incurring significant costs until the business case and social, environmental and economic impacts are studied. The rail alignment is only one aspect of any feasibility study, but it does play a crucial part as the backbone of the scheme, from which many other aspects depend. So just considering the sustainability aspects of a new project in the early stages, there's considerations from a BIM perspective to consider the CO2 overview early in the BIM project, the life cycle in terms of the construction and traffic, the CO2 emissions from that, comparing all route alternatives as an opportunity to influence, and finding coherence between cost and carbon emissions, and the workflows through the project life cycle. So investing in corridor studies then, key considerations such as passenger demand, journey times, frequency of rail services, and the overall capacity to move passengers and or freight between geographical centres. It all depends on having a rail alignment and an outline track layout to study. So once the initial corridor is established, it is often common for a project to be locked into this, except for relatively minor adjustments, improving the alignment within the corridor width in the following stages before construction. Therefore, the initial corridor evaluation and selection is an important task, and investing time and money at the start of a project often leads to a successful project outcome further down the line. So often in my experience, I've found that projects, small and large, can suffer from having a sort of quick and dirty kind of feasibility stage done initially, which kind of grows and grows in terms of its clarity, and that often is not a great way. It's far better to put the effort in at the start and to get something good at the start, and then not deviate too much from that as the life cycle of the project commences. That would be my experience, having done a few of these over the years. So one of the early activities is the procurement of a terrain model, and that model needs to be associated with good mapping. And these two things are important in the early stages of the project. So the requirements for a corridor study, the initial corridor study relies on finding an alignment which has as few conflicts with residential areas as possible, which is probably obvious, and seeks to minimise social, environmental, cultural and urban impacts. It also satisfies the minimum geometrical requirements for the project, and serves suitable intermediate and terminal stations, and keeps civil engineering costs to a minimum, and keeps carbon emissions to a minimum. So finding the the most cost-effective and environmentally friendly path through the topography are high priorities, but sometimes compromises need to be made to balance these two important considerations. So project classification. So up to now, I've talked very generally about building a new railway, but then of course there are going to be characteristics of the various types of railways that we're building. So high-speed rail is one. The geometry of existing highways and railways are sometimes difficult to follow due to the flat radius curves necessary for high-speed operations. Heavy haul freight lines, these have their own requirements as they are subject to relatively shallow gradients and vertical curve restrictions, which are necessary for the traction of long freight trains and with high axle loads. And then we have metros and light rail lines. Because of the slower speeds and more relaxed geometry constraints, it's common to be able to follow highways and roads into city centres to avoid expensive tunnelling and subsurface stations where possible. So these are very general things, but nevertheless important distinctions to understand between different rail systems. Some more corridor study considerations then. Investment in the latest technology available for finding the lowest cost path through the terrain can potentially save substantial capital costs. So modelling alignments across a virtual terrain with the capability of overlaying good quality digital mapping is considered to be best practice for initial corridor studies. So corridor exploration will lead to the development and evaluation of options. This is typically carried out as a multi-criteria analysis which considers the following. So that's engineering, capital cost, journey time, operations and maintenance, constructability and environmental factors, including carbon emissions considerations, are all factors to be considered. So this is a slide on specialist software applications. There are sophisticated modelling applications such as Trimble's Quantum, which is able to analyse thousands of alignments and rank them in order of cost to allow options to be shortlisted. So Quantum will simultaneously consider environmental, community, cultural heritage and hydrological impacts in parallel to consider the crossing of linear features, wetlands, floodplains and geological conditions. This is effectively a one-stop shop where the model is loaded with all the data inputs necessary to analyse the costs of each alignment and allows selected alignment output strings to be exported and used in other applications such as Bentley Rail Track or different Bentley products. So the image on the right is from Trimble's Quantum application. It's just an example there, just to show you what that looks like. So we mentioned inputs and outputs. This gives you an idea. So we've got the digital terrain model, the DTM, which we mentioned earlier, which is necessary for the software to work. We've got geometrics, which is the geometric parameters of the alignment, and that's the limits, the technical limits, the minimum radii, maximum radii, maximum cant deficiency, and that sort of thing. There's a whole list of geometric constraints which are necessary to put into the model. Cost and carbon unit rates. So that's basically to allow us to calculate once we know the volumes of a particular alignment, we can multiply those volumes by a unit rate, and that can be a unit rate for cost. It can be a unit rate for CO2. Depending on what the volumes are, it could be earthworks, it could be tunnels, it could be viaducts, etc. And then we've got constraints at the bottom there. This is another input, which is if you like, the avoid areas that you don't want to go, environmentally sensitive areas, or areas of high risk, areas which are geologically areas that you want to avoid, that sort of thing. So there's a lot of work you can imagine that goes in at the front end, and then you get that sort of turning of the handle in the middle, and out pops a whole range of different alignments, which will give you reduced planning, the ability to test all options, documentation about each alignment, the corridors themselves in terms of width and height and that sort of thing, and the ability to optimize the alignment, because it's not always the cheapest alignment that comes out is the one that's selected, and low cost and CO2. And again, we'll come on to that in a minute, but you can look at both and balance the two as required. And of course, the 3D input to design, and that is the chosen alignment string or strings can be exported from the model and used in the designs in other applications. And that process can be used at various stages of the project, scoping, feasibility, and then design, detailed design. So this example here on the screen is an example from a project in Norway. And if I can just point out, in this third column on the left-hand side here, we've got the cost, which is in kroner, and it's giving us the cheapest cost first, and then ranking all of these alignments, which you can see in the middle, color-coded by in terms of cost, but also with the red arrows are showing you for each alignment it shows you a carbon calculation, which is based on the unit rates for the different civil engineering activities, earthworks, tunnels, viaducts, etc., and also a calculation for traffic, and that is basically a something which Trimble have added into this modelling to allow you to look at what the impact of the CO2 emissions will be over the years once this line is built with that alignment. So it's a very powerful tool. The CO2 calculations are a relatively new addition to this modelling. The model has been around many years, but this is an add-on which is now giving the application a more powerful way of selecting alignments. And this bottom right, these are a blow up of the top three over on the left. So what it's showing is that the cheapest alignment, which is showing at 1.5 billion kroner, is not the best from a CO2 point of view. In fact, the third alignment is the best from a CO2 point of view, but it's another 50 million kroner more expensive. So as you can see, and the other thing is it's shorter, and there are other benefits to having a shorter railway, in terms of journey time and that sort of thing. So as you can see, there's a bit of a balancing act to be done here. It's not just the case of looking at the cheapest alignment. Certainly from a sustainability point of view, we want to be looking at the carbon output, carbon emissions, and that, if anything, may be a case for getting government funding in order to choose the lowest carbon footprint, for example. That might be one of the actions that might come out of looking at this, or it might be simply a case of choosing the best alignment from an environmentally friendly point of view. This is just a slide of that shows you again the latest quantum screen, showing corridor widths. They're quite thick lines there, but the corridors are are going to be wide, but it gives you an idea of the different options that you can look at in the model. So some of the assumptions that we have when we're building railways have been challenged over the years. You know, I mean, it was always the case that having a cutting instead of a tunnel was the cheaper of the options. But in actual fact, as time has gone on, this has kind of been challenged many times. You know, woodlands have been removed in the past to create cuttings for across the corridor width, and of course, you know that's quite a lot of the woodland area is removed in order to create the cutting, particularly if it's a deep cutting and it has to be stepped in order to deal with the stability of the cutting faces. So over the years, more and more we're seeing cut and cover green tunnels becoming more preferred alternative to decarbonise the project's carbon footprint. And that also enables the sequestration by the reinstated woodland cover over many years can significantly offset the carbon emissions from the cutting construction works. So replanting forests on top of the railway does allow that in time to come back and to be able to be a way of getting a credit in terms of the carbon overall carbon emissions. So cost reduction initiatives and innovations for cut and cover tunnel construction will give contracting organisations an edge at tender stage as clients prioritise decarbonisation proposals alongside tender price. And also looking at viaducts versus embankments. Viaduct construction is mostly unavoidable above a height of approximately 25 metres, 30 metres. But below this level, there is sometimes a choice between viaduct and embankment. From a carbon emissions perspective, the embodied carbon footprint in concrete production, including the steel reinforcement, is high. So there is currently research taking place in many countries to reduce carbon footprint in concrete production. Of course, not just for viaducts, for all concrete products. And the use of secondary cementitious materials, SCMs, to replace some of the cement in the concrete to lower the embodied carbon is a common initiative. Embankment construction is often lower cost and has a lower carbon footprint, but can also create a social barrier, which prevents free movement from one side of the railway to the other. So alternatively, viaducts allow this free movement as shown in the photo above. So photo above is the Dartford crossing, or where the railway goes under the QE2 bridge, artist's impression. But it shows you the freedom of movement under viaducts, and as you can imagine, embankments kind of create a sort of a boundary, particularly if they go through urban areas where you can end up with social differences between each side of the railway. Right. Okay. So we've kind of established that calculating carbon is becoming more and more important when it comes to building railways. And so at the feasibility stage, it was not common in the past to set a calculated carbon baseline for the project. However, this is now becoming best practice as it can drive significant reductions at the early stages of corridor selection. In other words, if you ignore carbon in the early stages of a project, it can come along later, and by that time it might be too late to change an alignment if it's determined that there's a more favourable alignment from a carbon perspective. So it is always better to look at this in the early stages alongside cost. So it can be taken forward as a baseline to later become a basis for clients and contracting organisations to develop realistic decarbonisation targets. So if clients know what the carbon baseline is for a particular alignment that's been chosen, then that baseline can be used when it comes to looking at alternatives and looking at contractors' proposals for building that alignment. They might be able to better some of the assumptions that have been made in the baseline, and that would be favourable to that contractor if they can do that. So carbon accountancy is growing in our industry, and there are already many carbon calculator tools available for the rail sector. And there's some quite well-known ones for existing railways at the moment. And I think as time goes on, there will be more and more information out there to enable unit rates for all sorts of different civil engineering activities to be taken as a sort of yardstick to be able to calculate for any project. So we are seeing the contracting market being asked more and more to calculate their expected carbon emissions as a result of their designs and construction activities. And it is anticipated that this will become an integral part of the tendering process for design and build contracts in the future. Okay. So we've talked a lot about decarbonisation, but of course there's environmental considerations are wider than that. And of course, we always have an environmental person looking at this whenever we do a particular project, and they're looking at the whole spectrum of the environmental considerations, and that would typically include protected forests and woodlands that are affected by the project, wildlife conservation areas, heritage sites, sites of a religious interest, and any city urban conurbation or industrially developed areas. And the image on the right there shows what an environmental engineer would be working with, and that would be an ArcGIS type application. And Esri is a environmental organization that provides mapping and layers of mapping which allow you to put the alignment across the mapping and switch on and off any one of these layers to enable you to look at the impacts of each at any time. So, okay, I kind of skipped through this because I've already mentioned this. I think I'm running a bit short of time. Right, geological considerations. So it's good practice to create high-level geological zones which group together geological conditions that have similar levels of risk and suitability. And the unit rate of carbon emissions and cost will vary according to the geological conditions. So this needs to be taken into account. So what this shows here is 4 zones. So this is a very general grouping together of between the sort of worst and best and the sort of mid-area conditions from a geological perspective and the respective color coding. So if you've got that in the mapping, it allows you to also look at the alignment with respect to whether it's going through a yellow area, green, rose or blue area, and what is the impact of that, and is often a driver for changing the alignment to, for example, to move it away from a zone 4, where you've got high sensitivity areas such as lakes, natural springs, areas of flooding and erosion caused by human activity. And then there's the hydrological considerations. Now, many countries have seasonal events resulting in significant surface and groundwater flows following periods of heavy rain, particularly in hilly and mountainous areas. So these can be areas that remain dry for much of the year and not easily identified from mapping. And terrain models without the expertise of a hydrology engineer, if you're not able to see water body, lakes, the rivers in the mapping, it may be because the mapping has been taken at a particular dry time of year. So there are occasions where flash floods occur and can be a problem for several days, and kind of when you look at the whole picture throughout the year, it's a small percentage in terms of the time, so the mapping might not reflect that, but it's extremely important to be able to be aware of these areas. So building railways across streams and rivers has to consider the worst case water flows, flooding, tidal waters. So modelling the extreme conditions is necessary before rail elevations are fixed. So how high up is the railway going to be placed to make sure that you've got sufficient flow of flood water and rivers, etc. And of course, climate change is causing incremental changes to the hydrological design requirements. As we go through the years, we're seeing more and more climatic extremes. So that has to be taken into account by an expert hydrological engineer. Highways corridors, it's good practice to follow existing transport corridors where you can, to avoid the widening of environmental impacts by placing alignments away from these corridors. However, this has its complications as highway intersection points, as shown here, become very complicated in order to thread the new railway through an existing intersection such as this. It can be done, as is shown here. If you look closely, there's actually two railways that have been built after this this cloverleaf intersection was in place. I know this is an artist's impression, but it is actually an existing highways intersection with the railway being shown as an artist's impression, and these railways were designed and built in this way. So it's possible, but if the alignments are okay in terms of the vertical curvature and the headroom that would be required in order to weave underneath and over the top of these roads, then that's fine. But some railways won't be able to do that, particularly high speed, where you've got the requirement for flat vertical curvature, flat curves, etc. It may well be impossible to actually build a railway through this system, and mean that it needs to be pushed out to the east or the west of this system in order to build it. So we've got a slide here on technical parameters. So first of all, high-speed rail, minimum curve radius in high-speed sections for 350 kilometers per hour is typically between 7,000 meters and 8,250, depending on what speed is used as the upper limit. Exceptional limits can be lower, but this should be avoided at the feasibility stage. I mean, it's sometimes necessary to adopt exceptional limits, so that's usually done in the detailed design or further down the life cycle of the project. So heavy haul freight lines, typically gradient limits are much flatter than for passenger lines, and restrictions are placed on vertical curvature where the longitudinal profile rises and falls within the length of a train. So this is all about traction of the freight train. Very long and heavy freight trains, can stall on steep gradients or gradients which have got multiple vertical curves, and so therefore it's necessary to be able to restrict the curvature to enable these sort of very long and heavy trains to to negotiate those alignments. Metros and light rails. So on many tram and light rail systems, the circular curves join the straight sections without a transition curve even. So allowable cant efficiency limits are high to keep the cant as close to level as possible, particularly in street running situations. And just to mention future proofing, because if a project wants to plan for a higher speed in the future, that is in excess of the chosen operational speed, then the curve radii will need to be flatter. And this constrains the alignment further. And this usually has a higher cost, and also it will have a higher carbon footprint as well if we want to future-proof it for a faster speed. And that all has to be taken into account at the very early stages of the project. Some track layout considerations. So at junctions on the left, there's a traditional flat junction with a diamond crossing. Diamond crossings are more onerous in terms of maintenance, with the two obtuse and two common crossings continually getting a bashing, and also there are maintenance issues off the back of a junction, particularly where the branch is curved, and we have to have a flat zero cant diamond. That can cause issues with twist off the back of the diamond, so therefore it can be a maintenance issue. To eliminate that layout, or to improve that layout, to eliminate the diamond, we've got a flat junction with a larger footprint, of course, but there's many benefits for speed and S&C maintenance. If you've got separate turnouts, like a turnout and a crossover, the turnout to enable you to still do the same thing, takes more space, but on new railways, if you've got more space, it's much better to do a layout like this to avoid the traditional diamond crossing flat junction. And then, of course, you've got the requirement for operational requirement to need grade separated junctions, which will allow conflicts to be removed, so that that you don't have one train waiting for another to pass over the junction before it can go in the opposite direction. It can avoid the up direction, can be completely separate from the down direction, if you like, in order to keep traffic flowing. Stations. So we've got some examples of stations. The intermediate station layout can have crossovers either side to allow the intermediate station to also be used as a terminal station in the event of blocking the line on one side or the other. We've got I've got a 4-platform terminal station layout. Again, typical crossovers, and a simple 2-platform for a tram, and then in that case the points sometimes you'll see will be self-acting, which allows trams to pull out of the platform into the head shunt, with the flange of the wheels of the trams actually operating the points, and then it sets back into the platform, and that avoids having to operate the points remotely. And then at the bottom of the screen there, we've got a typical 6-platform arrangement, which is showing perturbation layout for 4 platforms. So what we mean there is that if we get a problem with any of the points where they need to be clipped out of use, the blue layout at least allows 4 platforms to stay in use. We don't like using scissors crossovers with the diamond in the middle, but if it's only for perturbation reasons only, then it doesn't get much use, and therefore it's relatively low maintenance. So it's acceptable as a perturbation layout. So it gives you an idea of the things you can do in a terminal station, and this, of course, all of these things have a knock-on effect for the footprint of the railway. And in order to have the most efficient footprint, which is also going to be beneficial in the long run in terms of operational needs. Okay. Just a slide on S&C types. So switchings and crossings can be an early consideration where they're located at junctions. In my experience, this has not been the case on many projects. To look at the type, the S&C type, very general sort of kind of junction arrangements without really thinking too deeply about the types. But the footprints of the turnouts, they can vary a lot, and obviously due to the turnout speed, they can vary, and also according to the supplier for the same speed, they can vary. The geometry of the diverging paths can vary depending on the supplier. So all these things really lead me to always advise that these things should be looked at early in the early stages of projects. And when it comes to procuring contracts for building civils and track, I would always advise to not delay the procurement of the switches and crossings contracts, because they can have an impact on the civils design. You can imagine here, as this image shows, that if you've got more than one option for the same speed junction layout, that the footprint of a viaduct, for instance, let's say this junction was on a viaduct, then you would need a different design for that viaduct if you had a different S&C supplier. And you could build for a footprint which is like a catch-all, which means it would accommodate both suppliers' geometries, but then that would be more expensive and more carbon emissions. So it's always good to think about these things and to consider the S&C procurement at an early stage and not leave it to further down the line. Rail expansion devices is another one, really, which it's good to think about in the early days, because when you have an alignment, horizontal and vertical, it's good to think about whether the alignment is curved or on a straight in the places where the rail expansion devices will be placed. Because what we want to try and do is avoid putting rail expansion devices on curved and canted track, because that becomes a maintenance headache. So it's always good. I mean, you can see the example here of where the rail expansion devices are on curved track. And yeah, you will find a number of examples if you're looking into this deeply, but basically, if it can be avoided in the early stages, it's much better to try and place the ends of viaducts on straight track and not have a curve like this, if it's actually possible to do that, thinking more about maintenance further down the line. And then we get into track form considerations, slab track versus ballasted track. And ballasted track is considered to have a lower carbon footprint and a lower capital cost at the construction stage. But then the ongoing maintenance of ballasted track, for example, using on-track machines, tampers, etc., can increase the whole life costs of the carbon footprint. Whereas slab track, you don't need to tamp it, obviously. So, there's a saving there in terms of whole life carbon footprint. The slab track is a low maintenance option and has been adopted on many railways in preference to ballasted track. And when we get into slab track, we've then also got the option of choosing precast versus in situ. So this gives you an example here of the difference between the two. And if a precast track form is selected, there's more potential for reducing the carbon emissions in a controlled factory environment compared to pouring concrete in situ around the sleepers on site. So this is something we looked at on HS2 particularly, and found that there is a benefit to the precast in S&C and plain line. A final slide then, just also on track form. Yeah, so after rail, concrete sleepers are actually the second highest embodied carbon material in track. So composite sleepers have been more recently developed, and they're made from a low embodied carbon material using waste plastic recycling, and deliver a substantial reduction in embedded carbon. So they're approved now for mainline track depots and metro systems, and I think we're now starting to see a lot more use of this type of sleeper in preference to the concrete sleeper where we can, particularly in depots and low category routes. So that's the end of my presentation. There's probably about 10 minutes left for questions. Yeah, thanks very much.
That was brilliant, Phil. Thank you very much indeed for your presentation there.
Yeah, thanks.
It was. I could ask the group that if they've got questions to pop them in the chat, please. That would be good from our perspective. A few points I was quite interested and picked up on through that presentation, Phil, was just how critical it is to get that corridor correct in the start. The way that actually impacts the whole budget for the project was an interesting point of note for me. It's also something else I picked up on was the sort of topical nature of quantum software, including a carbon calculator, which makes it pretty handy tool for measuring just what's going into the project. Also the hydrological considerations with the way the weather's been going lately, and certain events in the recent past, it's more prevalent now, the way that global warming is having such an effect on the railway. So that's good that that's included. The other point I was also quite interested in, and I hadn't really thought about before, was that of the choice of your S&C, how that can then impact the cost and the carbon footprint of the project by having to redesign a junction and provide more infrastructure to accommodate a particular choice of S&C. So yeah, those were the sort of highlights for me, and that was actually quite a fascinating talk, so thank you very much indeed, Phil.
Yeah, thanks, Peter. Yeah, much appreciated.
Okay, I don't actually see any questions popped up in the chat, so we'll just hold on a sec there to see if anybody else does come up with anything. So thinking also about that presentation, I was quite fascinated that the way that you can actually thread an alignment through a motorway junction or something like that. It's fascinating to see it in this area where HS1 comes out and sort of weaves its way through the Kent countryside, sort of diving in and around motorways. It's good, and also, having driven up and down these roads, it's quite fascinating to watch the trains go flashing past you as you're driving through the junction. Just thinking about that, is the distraction of a train considered in the design of a junction, or sorry, not a junction, in the way that a line is threaded through a motorway? Is there any consideration for how that can distract motorway traffic?
Yeah, I think Yeah, I mean, I've often gone through Dartford Tunnel and tried to see if I can see, because when you go through Dartford Tunnel, you go underneath HS1,
Yeah.
and you can never see the train, because when they built the the low viaduct, which goes over the top of that direction, but underneath the QE2, if you know what I
Mm.
mean, you can't see it. And I think when you're actually on the bridge itself, again, I don't think you can actually see the railway from the bridge.
Mm.
I might be wrong there, um, but yeah, I mean, I think it's definitely both. You know, it's considered for both the the train driver and for the motorist,
Mm.
in terms of putting up sort of extending the walls on either side of the railway or barriers, in order to make sure that there's no distraction. Um,
Mm.
there's
Okay.
plenty of other sort of distractions, but yeah, that was
Yeah, certainly are.
I definitely know that is considered. Yeah,
Excellent. We've
yeah,
got a question from Sandeep asking, does software such as Quantum take into account the expected lifespan of each proposal option into its CO2 calculation?
yeah. So the lifespan. I mean, certainly, usually when you're building a new railway such as this, there's always going to be a sort of minimum life expectancy of the structure that's being designed, and so that would be irrespective of using quantum or not. There would definitely be a requirement, and what quantum does is it considers a kind of a very general assumption about the civil engineering works, so
Mm.
it won't go down to that level of detail that would determine the type of structure or the integrity of the structure from its life cycle point of view. But
Mm.
I think just purely in order to minimize civil engineering works, so often if you can do that, then it does by default, it kind of increases the lifespan of that particular earthwork or structure if you can
Sure.
minimize it by having an alignment which is kind of um, still respecting the limits, the geometric limits, but also minimizing the cost and civils. So it's a good question, actually. But yeah, I think it's not a quantum question so much as a more sort of general question.
Mm. Okay, thanks very much.
I hope that's answered it, Sandeep. Yeah. Okay.
Yeah, wonderful.
Okay.
Yeah, great, thanks. There we are. We've got a response. Okay, I don't see any other questions popped up, so just remains for me to propose a vote of thanks to you, Phil, for quite a thought-provoking presentation, and it was a good pace and enabled me to absorb most of what you were saying. So some presentations are at warp speed, but this was good. So thank you very much for that being paced well. That was good.
Yeah, no, it's a pleasure. Thanks very much.
So, folks, thanks very much for joining us, and do check in for further presentations throughout the year. So great. Thanks very much indeed for your time, ladies and gentlemen.
Okay. Thanks a lot.
Thanks.